Welcome to our Year 10 video on acceleration. This is the fourth video of our series on forces and motion. Here are our learning intentions for this section. Okay, learning intention number 1. Interpret the motion represented on a speed time graph. So in our previous video, we looked at distance time graphs. Now we need to think about these speed time graphs and think about the story that they're telling us. So here we go. We start at the origin of the graph here. Okay, and at this point, we're on 0 seconds and 0 speed. Now we move from here up to point A. So what's happening here? Our speed is increasing as time increases, and it's at a nice constant increase, okay? So if our speed is increasing over time, we're actually accelerating here. So we're accelerating. Now, along here, time is increasing, but our speed is staying at 10 meters per second. So here we're driving at a constant speed. So we're accelerating here, and now we're driving at a constant speed. Okay, what is happening between B and C? So, time is increasing and the speed is decreasing. So we're decelerating here. All right, from C to D, there is no speed, but time is increasing. So we're stopped still. We're staying still here and time's increasing. Okay, and then up to E, our speed is increasing as time increases, so we're accelerating to get our constant speed between E to F. So let's think about it. All right, so we've left home and we're walking along, and our speed is increasing until we get to a nice pace that we like, and then we walk at a constant speed until we get to this point B, where we start going up a hill maybe, and we decelerate. We start going slower till we stop. We get to the top of the hill and we're puffed out a bit. So we stop, and then we start to walk again. We accelerate up until we get to a constant pace, which is a bit less than we were on before. Okay, now if we looked at our graph, we could actually talk about that in our units. So our highest pace was 10 meters per second, but our more relaxed pace was only 5 meters per second, so half the pace of our higher pace. So what you need to be able to do is look at our graphs, whether it's speed time, distance time, and tell the story of the graph as such. Okay, this speed time graph, this is just showing a constant speed. Okay, so time's increasing, but nothing's happening with the speed. So it's just a constant speed. Now, I really love these three because they make you think. So the top one is a position time, which is our distance time graphs. The bottom one is our speed time graphs that we've just looked at. The middle one's velocity. They are showing the same set of occurrences. And what that is kilometers per hour. Okay, so it's me going for a bike ride. Okay, so position time. It takes me about 0.25 of an hour to cycle 3Ks, and then I cycle home. So I start at home, I cycle for 3 kilometers, and then I cycle home. That takes me half an hour, okay, to do my 6 kilometers. Might be a little bit quicker than I usually go, but never mind. So half an hour to do 6 kilometers because we've gone 3Ks there and 3Ks home. All right, ignore the middle graph for a second. We'll get to that. Speed. Now, because I'm such a wonderful cyclist, there was no hills or anything. I cycled at a constant speed. So I cycled at 12 kilometers per hour. Okay. And it took me 0.25 of an hour to get to my turnaround spot and then the same home. But because it was nice and flat, my speed didn't increase or decrease at all. Alrighty, this one, velocity. Now, velocity is speed, but with direction. So if you look at this, my first part of my journey, constant speed, so it's straight. But then we switch down to the opposite side of the graph because we have direction involved, and this is my journey home. So this vertical line here is me turning around to cycle all the way home again. So you just need to learn to tell the story of the graph, to read the graph. All right, learning intention number 2. Once you can read the graph, we need to be able to work the gradient of the speed time graph out to determine the acceleration of an object. So you've done gradient in maths, okay, and it might be something that makes some of you think, oh, I don't like doing that. That's cool, that's why we practice, okay? So the average acceleration, that's our gradient, so it's our m in maths, is the change in speed, which is our rise, divided by the time, which is our run. Remembering what we mean by rise and run, okay, so rise divided by run, this would tell us our slope is 0.5, so our acceleration, if we was looking at acceleration here, would be 0.5. Okay, same here. So in the previous graphs, in our distance time graphs, we was looking at speed. Because here we're looking at speed time graphs, we're now finding acceleration when we find the gradient. So you might want to put this on your formula sheets or whatever you're making where you take notes. If it's a distance time graph, to find the gradient, you're finding speed. If it's a speed time graph, when you find the gradient, you are finding the acceleration. That's how you find it. Sorry, that previous slide, if it's a negative slope, okay? So if you're looking at something that's decelerating. Okay, learning intention number 3. Calculate acceleration in meters per second, and you'll see when we're talking acceleration, we're talking the exponents -2 compared to the -1, which was our speed. Okay, now don't get freaked out at this formula. Acceleration equals delta velocity divided by delta time. Delta just means changing, so change in velocity, or we might be saying change in speed, divided by change in time. Okay, so don't panic, we'll go through all of this. Remembering, if we're talking about acceleration, we're using these units. So if you see those units, you know it's acceleration. Now, in all of this, there's different language we're bringing in. We talk about speed, we talk about velocity. Now, I'm not going to say they're the same thing because they're not, but you can interchange them, okay? So basically, speed, I could be talking 13 meters per second. Velocity is your speed with direction, so it's 13 meters per second south. Now, when you're using if you're doing the acceleration calculation, you just need the 13, okay, the 13 meters per second. In the acceleration calculation, it doesn't matter about the direction as such, all right? So don't at the moment get hooked up on the fact that you might see velocity. If you see velocity, it's just asking for the 13. All right, let's have a think. We've got this equation. What do all these symbols mean? So the A is acceleration here. That triangle is delta, and that means changing. V, here it means velocity. In this scenario here, it's the final velocity, because, so T is time. The U is initial velocity. So because we're looking at the change in velocity, we're looking at the initial velocity, the final velocity, take away the initial velocity. Okay, so the final speed, take away the initial speed if we're doing speed there. So here it is just using speed instead of velocity. So I just need you to relax to know that you can use speed or velocity to find acceleration. And time is the change in time. All right, so let's have a think about my Toyota Corolla. It's going to take 2 minutes to get from 0 to 90 kilometers an hour. What is its acceleration in meters per second? Ignore the H, you'll see why I've got that there, because if you remember in a previous video, I had seconds by accident there and I put the H in to cover it. All right, so we need to remember this from the last video because we may need to use this. To convert kilometers per hour to meters per second, we divide by 3.6. And to convert from meters per second to kilometers per hour, we multiply by 3.6. So some of these little calculations you just need to have in the back of your mind. So, my formatting hasn't worked, but I'll talk you through it. My Toyota Corolla takes 2 minutes to go from 0 to 90 kilometers per hour. What is its acceleration in meters per second? First up, I need to convert 90 kilometers per hour to meters per second. So, as per the previous slide, we go 90 divided by 3.6 equals 25 meters per second. Right, we now need to convert the 2 minutes to seconds because we need everything in meters and seconds for what we're doing. So we had 2 minutes, so 2 times 60 is 120. Right, now when we think about that formula we need to use, we need our change in velocity. Okay, we're using speed here, so our change in speed. Okay, my final speed is 25 meters per second. My initial speed was 0, so I'm saying 25 minus 0, so my change in speed is 25 meters per second. My change in time, it took me 2 minutes to get to that. Okay, so it's 120 minus 0, 25 divided by 120. So my acceleration was 0.21 meters per second. Geez, my Toyota Corolla goes fast. Okay, so there's our formula that we've just used. Okay, that's what we've stepped through. Alrighty, let's look at this in practice. We've seen it written there, but we've got these two cars. We've got the yellow one and that red Porsche. I don't know what the yellow one is, not too good with my cars. So both started at 0 meters per second. Yellow car got up to 29 meters per second, whereas red car got up to 29. They both got to 29 meters per second, but it's the time that's different. Okay, the yellow car took 10 seconds to get there, whereas the red car only took 4 seconds. Alrighty, so we use our calculation. For the yellow car, we're finding that change in acceleration, 29 meters per second, take away 0 meters per second. Okay, so 29 divided by 10 gives us 2.9 meters per second. And here we're doing it for our Porsche. So our Porsche accelerates at 7.3 meters per second. Okay, now if we just go back to my car, I said my car was slow. I said my car was fast. Is my car fast compared to these? No, my car's slow. It's my acceleration that's slow. I would just like to add that for the sake of my Toyota Corolla, I made all those numbers up. She'll get offended if you think she's slow. All right, take it easy, guys, and remember to subscribe to my YouTube channel.